Okay, it is the second part of section 7.3, integrals of hyperbolic functions. Here we have a formula for integrals of hyperbolic functions. That is opposite operation of derivative. Derivative of sine hyperbolic is same as now cosine hyperbolic. So integral of cosine hyperbolic must be sine hyperbolic plus a constant. Exactly that came from the derivative formula of hyperbolic functions. And the same way here we have a formula for integrals of inverse hyperbolic functions. That came from the formula for derivatives of inverse hyperbolic functions. Again, for these formulas, don't try to memorize. If some of them are required, then you may look at a table. Okay, here, let's try to evaluate the integrals. Now, rather than x, we have 2x for sine hyperbolic function. So now, however, anyway, except a constant, it must be same as now cosine hyperbolic, right? So it'll become here cosine hyperbolic of 2x times some number here, n plus c. We have to decide this coefficient. Now, in order to do that, if you are making here derivative for this part, then that will be same as now sine hyperbolic of 2x, and here 2x must be differentiated. So that is 2. So we have extra 2. So if you put here 1/2, then these 2 will be cancelled out. So here half cosine hyperbolic 2x plus c is the final answer. Let's go to this one. Now, for this one, the same way, in the formula sec hyperbolic squared, its integration is same as tangent hyperbolic of x. Okay, so here that is now some coefficients. Let's put here now, and then that is tangent hyperbolic and x minus 1/2 n plus c. Now you will have to decide this coefficient, and if you are trying to make a derivative, then now that will be sec hyperbolic squared x minus 1/2, and then its derivative is 1. So there's so that 1 is okay. So that you may ignore this box. So that is the final answer. Now for this one, now we may try to use a change of variable substitution. For example, here u equal natural logarithm of t. Then from this one, du equals same as 1 over t and dt. Okay, so we have here 1 over t dt, and t equal 1 means here now u equal 0, and t equal 2 means that u equal logarithm of 2. So here this integral is the same as now from 0 to logarithm 2, and then cosine hyperbolic will be changed into cosine hyperbolic. Rather than logarithm t, we are using u here. And then now 1 over t dt is the same as du. Okay, we have that. Now the integral of cosine hyperbolic u with respect to u is same as sine hyperbolic u, and u is from 0 to logarithm 2. So that here, that is now sine hyperbolic u, which is logarithm 2 in with the upper limit, and lower limit u equals 0 will make a 0, so that this will be the final answer. Okay, now we'll evaluate the integrals by using the format here given integrand looks like here sum of around there, right? So we have to match the format. Anyway, for the first one, now if we pull out the 16, then outside will become 4, and or just 4 is coming out, then because we have to match the format over there. So let's look at that one. Then because it's a squared plus x squared, so exactly rather than only this portion is the same format, so that let's try to match the format. Okay, so that is now integral from 0 to 2 square root of 3, and then now here 1 over, okay, 4 will come out to become 2, and then here square root of now 4 plus x squared dx. Okay, so from this one, now we have half, and then for this portion is antiderivative is here now. A is now 2 squared, which will be 4, so that is same as inverse sine hyperbolic x over a. So that is now inverse sine hyperbolic x over a is 2, and then we are evaluating from 0 to 2 square root over 3, right? You can finish yourself the computation. Now there is now 1 over 1 minus x squared. Okay, let's look at formula again. That one looks like this one. Now 1 minus x squared, but we have two different cases. Once a is larger than x, a squared is larger than x squared, then we'll use this one. If x squared is larger than a squared, then we'll use that one. Okay, let's go back to the problem. And then now for this one, here x is moving from 0 to 1/2. That's a squared. So a squared equal 1. Now if we compare with x squared, x must be between 0 and 1/2, so that is larger, right? So here now a squared is larger, then we have to use that one. That is same as 1 over a, inverse tangent hyperbolic x over a. So we have to use this part. Okay, what is a? A is 1. So that here that is same as 1 over a. So a is 1. So that we know that. And then that is now inverse tangent hyperbolic x over a. Now a is 1. So that here now from 0 to 1/2. Right? So you can finish the computation. Okay, for this final one, and now it looks like that is major format is 1 plus something squared inside of the radical. So the format is now around this one, or x is there, so either this one or that one, but it's not x here, so that we need a little bit of manipulation. Okay, and substitution, u equal logarithm x, then du equals same as 1 over x and dx. Okay, 1 over x dx is now du. U is 1, then, no, x is 1. Okay, here, low bound of x is 1. Then here, logarithm 1 is the same as 0. And now, x is e. Then here, logarithm e equal 1. So your given integral is now from 0 to 1 in u integration. And this portion is the same as 1 over square root of 1 plus u squared, and 1 over x dx is the same as du. Okay, we have that now. Now, along with this integrand, let's go back to the formula. Then it's the case with a equal 1, so that there must be sine hyperbolic inverse x, right? So there must be here inverse sine hyperbolic of u, and u is from 0 to 1, so that is sine here hyperbolic, okay, inverse of 1, right? And once it is 0, then the value must be 0. Okay, so that's the final answer. Now, for inverse hyperbolic functions, and we can rewrite in this way. Since the hyperbolic functions can be written in terms of exponential functions. It starts with combinations of e to the x and e to the minus x, so that it is possible to express the inverse hyperbolic functions in terms of logarithms. So this one is now here an expression of inverse hyperbolic, each of inverse hyperbolic functions. Okay, so again, don't try to memorize it. Just if you need that, then by using this expression, you can express explicitly the inverse hyperbolic functions. Okay, that is the end of the section 7.3. Thank you.